Welcome back to the second part of lecture 4 of our antineoplastic agents. In the first part, we discussed agents which inhibit tubulin polymerization. That's gone. For the inhibitors of signaling pathway, we're going to keep that for next week. So instead of having a full 1 hour lecture this week, I'm just going to give you 2 parts, part 1 and part 2, because you have a test next week, and next week I'm going to give you the 3rd part, but we're not going to be calling it lecture 4 part 3. It's going to be lecture 5. I also updated the introduction to reflect the change. So inhibitors of signaling pathways, that's going to be next week, and that will leave us with agents which inhibit tubulin depolymerization. Okay, as we said, agents which inhibit tubulin depolymerization for this part. The well-known example of these agents is the paclitaxel, or which is called the Taxol. It's an important anti-cancer agent. Okay, other analogs of the paclitaxel like the docetaxel, cabazitaxel, the BMS 188799, the BMS 184476, and the orthotaxel, which are all analogs of paclitaxel. The term taxoids is used generally for paclitaxel and its derivatives. All of the paclitaxel is a natural product that was isolated from trees. The problem with paclitaxel is that you need 2 trees just to isolate enough amount to treat 1 patient. It's an effective anti-cancer agent, but that's the problem. So for each patient, you need 2 trees. That's why they moved to total chemical synthesis, and the chemical synthesis was established, the total synthesis. But the problem with the total synthesis, it was they got the total synthesis with 30 steps, and that leads to low overall yield. Okay, so they thought about what is called semi-synthetic pathway. The semi-synthetic pathway that you start from a starting material, which is a natural product that you got it from a natural source, then you add to that part, or you modify it to make the final product. So it is semi-synthetic or semi-synthetic, and that is what is being used nowadays. Okay, taxoid are found to bind to the beta subunit of tubulin. If you remember from the first part, we said that tubulin has 2 units or 2 subunits, the alpha and beta. So paclitaxel and the other analogs bind to the beta subunit of tubulin. The Taxol accelerates polymerization and stabilizes the resultant macrotubules. That is how it inhibits the depolymerization process. Okay. This is the structure of Taxol. You see, it's a complex molecule. It has been found that the acetyl group and the benzoyl group at carbon number 2 and carbon number 4, as you can see them here from the structure, these are important for activity, as well as the oxetane ring and the side chain. All of these are important for activity, which means you cannot change those if you want your compound to be effective or active as anti-cancer agent. So that, and as you can see also from the structures, all of these groups are in the lower part of the molecule, the southern part of the molecule. We can point that out. So if we can split the molecule into half, so these important groups are in the lower part or the southern part of the molecule. Not like, but the top part, you can change those to make better analogs that has better bioavailability, better better oral bioavailability, better water solubility, and better pharmacological activities. Okay, and that led to the discovery of the second generation taxoid. Those second generation taxoid have been found to be 2 to 3 times, or sorry, 2 to 3 fold better activity than the taxol. Okay, they have found that if you add, a hydrophobic group on the hydroxyl at carbon number 7, that will give you better activity. Also, if you put a suitable acetyl group at carbon number 10, that will improve activity, and not only improve activity, but make the compound resistant to the beta-glycoprotein, which is a pump that's found on the side, the cell membrane. This pump pumps out the anti-cancer agents before they give their effect, okay, which is a resistant mechanism for the cancer cell. They found that if you change the acetyl group at carbon number 10, if you put a hydrophobic group on this hydroxyl, that will give you better agents, as you can see here. So replacing the aromatic rings of the paclitaxel with other hydrophobic group improves activity. The addition of a methyl substituent at the 2' carbon will prevent the rotation of the 2', 3' ring. As you would know, this will make the molecule more rigid, and this will prevent the rotation that will give you the better analogs. Okay. Also, having a suitable, as we said, suitable acyl group at position number 10 will improve activity and make the compound resistant to P-glycoprotein, as well as acylating the 7-hydroxy group with a hydrophobic group improve activity. That results in analogs of the paclitaxel, as you can see from this structure, which shows you the docetaxel and the cabazitaxel. The only difference between those is the R group. In the docetaxel, the R group is hydrogen, these 2 R groups, and in the cabazitaxel, the R group is methyl. Also, it differs from the paclitaxel in that they change, as you can see at the top, they change the ring with a hydrophobic group. And it's not aromatic, it's aliphatic. All right, other examples, as we mentioned earlier, the BMS 188799 and 184476. These are other examples on the variations that you can use. Okay, you see here this one, the R1 is either O-methyl or methyl. You cannot change it that much, because as we said, you cannot change the lower part of the molecule a lot without losing the activity. Okay? But you can change that top R group. The orthotaxel, which represent the first orally active analog of the paclitaxel, the taxoid, It has this group here, and they change both. You can see in the original structure we have aromatic rings, this one and that, but in the orthotaxal they just change them with aliphatic groups. That gives better activity and lower the resistance of cancer cells toward the taxol. All right. Other examples on natural products that act as inhibitors for tubulin depolymerization are the iliotropin, and the epothelone. You see from the structure here the iliotropin and the epothelone A and B. The only difference between those is the R group here. Both of these are natural products. It has been found that these act as the same mechanism as the paclitaxel. All right. The important thing about these agents are that for the epothenones they don't appear to be substrate for the P-glycoprotein efflux system, which means cancer cells that have some resistance to paclitaxel will eventually be sensitive to epothenones. Also, they have better aqueous solubility than paclitaxel, which means that you can make better formulations, okay, maybe oral formulation. But the cons for the epothenones that the cleavage of the lactone ring by esterases, and it has been found that they are highly toxic in animals. So what ring? It is this part of the molecule. As you know, if you have an ester group inside a ring, this whole ring will be called the lactone ring. Okay, but because this is an ester group, it's going to be sensitive to hydrolysis by esterases, right? So that's one of the disadvantages of the epothenones, which is the cleavage of the lactone ring by esterases. So what they did, they came up with analogs like the ixabepilone. The ixabepilone, they change this oxygen from a lactone to an amide, NH. They put NH. As you know, the amide is what? The amide is resistant to hydrolysis by esterases. Also, since this R group is methyl, so the ixabepilone is actually an analog of the epothelone B. Okay? And again, if you have any question, you can ask this week, during this week. Okay, because next week you have a test. I'm not going to be answering questions. All right? Other examples on natural and synthetic products that act as inhibitors of the tubulin depolymerization, like the sarcodectine A and B, these which are analogs of what? Analogs of the iliotropin. Okay, and as you can see here, the eriboline, which is a synthetic analog of the natural product helicondrine B. You see the helicondrine B here. It's a very big, complex molecule. They made an analog of that. They just took this group because they found that this group is important for activity. So they took this group, modified it, and make this synthetic analog. And now the eriboline is approved as anti-cancer agents in the United States, Japan, and Europe. this is the end for the second part. And as I said at the beginning, there will be no third part. The third part, I will upload that after your test. Okay, so after you finish your test, you will find the third part, which is not going to be called part 3 anymore. It is going to be called lecture 5. And thank you for your listening. Goodbye.